Good morning. Happy Wednesday slash Thursday, whenever you're watching this. Um, so today I will get up some of the most commonly missed test questions for you so you guys can see that. Um, there are a handful of you, 4, 5 of you that still haven't taken the test. That's really important. If you can get that done this week, I can put it in for your quarter 1 grade. Um, so that test alone is causing a couple of you to be failing right now, and we don't want that. So make sure that you're getting in there and getting that done. All right, so today we're going to talk about bonding a little bit, and these are all of your success indicators, okay? So this is a thing that the school asks of us, so you guys should have your success indicators for stuff for learning in class. So basically today we're going to be talking about chemical bonds, how you know if it's ionic or covalent. We'll get into molecular shapes just a little bit, and then next class we'll really start talking about like Vesper theory and stuff. So some of this will apply more for next class. So today we're going to talk about chemical bonds. Okay, so we know that chemical bonds are going to be the attraction that holds your atoms together. So these can be formed or broken in chemical reactions, and that only the valence electrons are involved. Okay, so unless we're talking about just a metallic bond. So metallic bonds, we touched on a little bit last class, but they kind of have a different set of rules for bonding because they involve their outermost shell and the next one in. So everything else that we're just talking about the outer shell electrons. So if we're looking at this diagram down here, we have 2 atoms, and we know that overall the electron cloud will have a negative charge, and your nucleus would have, or your nuclei would have more positive charge because of the protons and neutrons. So only the electrons are going to be involved in bonding. They want to bond because of the octet rule. Okay, so we know this already, that if an atom has 8 electrons in its outer energy level, that it's going to be stable and it will not lose or gain electrons. So anything in the noble gas family, they're already stable. They already have a full outer shell. They make up the octet rule, and they're not going to gain or lose anything. So everything else wants to become stable. So if you're looking at something in the halogen family, so it's group 17, or the oxygen family, those are going to be wanting to gain 2 or 1 electrons. Anything on the left-hand side of the periodic table, like the alkali metals and the alkaline earth metals, they only have 1 or 2 electrons on their valence shell, so they're looking to get rid of those so that they can become stable. Because if they lose their outer shell electrons, it kind of really goes back down to the next stable ring. So that's your octet rule. Every atom in bonding, the goal of that is to make both parties stable. So this is also how we get oxidation numbers. Okay, so oxidation numbers, we've already talked about this a little bit. If it's an ion. So we've been working with ions for a while. We just haven't called the oxidation numbers. So whenever you are writing the plus or minus for an ion, that's the oxidation number. That's how many electrons atom's going to gain or lose. Okay, so if you have sodium only has 1 valence shell electron. So it's not going to gain 7 electrons. It's much easier for it to lose 1 to become stable. So it's going to lose its 1 outer shell electron, which would give it an overall charge of +1. On the other end of that, so like the right-hand side of your periodic table, these are going to be gaining electrons. So if you look at the carbon family, those have 4, so those can kind of go either way depending on what they're bonding with. But like nitrogen family, oxygen family, halogens, those are all going to be gaining electrons because they're already close to 8. They already have 5, 6, or 7 valence electrons, so they're not going to be losing their electrons, they're going to be gaining them. So if you have oxygen, for example, it has 6. It needs to gain 2 more to become stable. So if it gains 2 more electrons, it'll have an overall charge of -2. So how you know what type of bond you're going to get is what we use the electronegativity trends for. So the electronegativity we talked about last class is the attraction a bonded atom has for electrons, and the difference in electronegativity is going to help determine the type of bond. So your periodic tables, if you're using ptable.com, just the letter P, the word table.com, they have the electronegativities on there. There's also electronegativity charts. If you search that, there's electronegativity periodic tables. So you'll be looking at these, and you can see that these numbers on here are, it's not the mass number, it's not the atomic number. These are the electronegativities. So what you should notice is that in the top right-hand corner, kind of where fluorine is, those are going to have higher electronegativities, and as you work your way down and across over to the left-hand side, you're going to have lower electronegativity. So these are going to be talking about, like, the higher the electronegativity, the more likely that atom is to gain electrons, and the lower the electronegativity, the more likely that atom is to lose its electrons. So you're basically looking at anything below or over 4. So if you have 3 valence electrons or less, it's easier for that atom to give up those outer shell electrons to become stable than it is to gain 5. So if you have 5 valence shell electrons or more, it's going to be easier for you to gain those extra electrons rather than give up all of those other ones. So for ionic bonding, okay, we're going to talk about, here we go. One type of bonding, we're going to talk about ionic bonding and covalent bonding. So ionic bonding, these are going to have the biggest difference between their electronegativities. So that chart that I just showed you, you'll be comparing those numbers, finding the difference between them to determine whether it's ionic or covalent, and then polar or nonpolar. So with ionic bonding, you're bonding together a metal and a nonmetal. Okay, so typically this is something that is coming from the left side of the periodic table and the right side. So you have 2 atoms that are on opposite sides of the periodic table. These ionic bonds are going to have really high melting points. They're going to have really high boiling points. And the reason for that is that they're very strong bonds. Okay, so you get a very strong bond between, for example, an alkali metal and a halogen, because the halogens have very high electronegativity. So they are stealing the electrons from the alkali metal. So they are having a very, very strong bond together. Ionic bonds will also conduct electricity if they're dissolved in water. So that's one of their physical characteristics. So if you dissolve like salt in water, so that's what this picture is here in the middle with the sodium and the chloride, that's table salt. So if you dissolve salt in water, it will conduct electricity if you ran electricity through that solution. And they form a crystalline structure. So that's important to know. Ionic bonds are going to give you crystalline structures. And the reason for that is because it's such a strong bond. So when you get a crystalline structure, you get a regular repeating pattern to the bond structure. So the other small picture right here, that's like an up close view of salt. So this is the molecular diagram of the arrangement of those molecules, and this is an actual photograph. So with the ionic bonds, the atoms are going to give and take electrons. So your cations are going to be giving up their electrons, and the anions will be taking the electrons. Whoops, there we go. Here, the delta En, so that's the change in electronegativity, needs to be, or the difference in electronegativity needs to be greater than 1.8. Okay, so if you went back, let's go back here to this periodic table here, and we had sodium and chlorine there. So chlorine is here with a 3 for electronegativity. Sodium is 0.9, so the difference in electronegativity between these is 2.1. So that fits this. No, I can't do it right now. Oh, sorry. Somebody just came in. So that fits this requirement of greater than 1.8. So here's just some more pictures of this. Sodium, so like we said before, this is just showing the valence shell electron. Sodium has 1 valence shell electron and chlorine has 7. So because this difference in electronegativity is so high, chlorine is going to steal that electron from sodium. They're not sharing. Chlorine is taking that electron away. So then these two are going to be bonded together because it has taken its electron. This is another way that it shows that. So if you look at this too, this also shows kind of what your Lewis dot structures would look like for that. So if you look on the left-hand side where it has the red sodium and the blue chlorine, you can see where the electron has moved from sodium to chlorine. So when we are drawing these out, you're going to be drawing their Lewis dot structures and then either circling the electrons to represent that they're sharing, or we'll be drawing arrows to show that they are being transferred. So in an ionic bond, you would draw an arrow to show that that electron was transferred from sodium to chlorine. Okay, so let me see here. Here again, this is just another example of this. I need to change the color of these dots. Wow, that's hard to see. Okay, so electrons are going to be lost or gained, and that's going to result in the formation of an ionic compound. So here, another example, we have 2 fluorines and 1 magnesium. So fluorine has 7 valence shell electrons in either one of these. So they each need to gain 1 electron. Magnesium fills that void perfectly because magnesium has 2 electrons to give up. So 1 will go to this fluorine and 1 will go to that fluorine. So in the end, this magnesium ends up being the cation, okay, because it's going to lose 2 electrons. It's going to have a charge of positive 2. So this magnesium would have an oxidation number now of positive 2. And then each of these fluorines would have an oxidation number of negative 1 because they're both gaining an electron. So because of that, we'll start talking about bonding names and structures a little bit. So because of that, you can see down here this says MgF2. So we know that this magnesium, in order to bond, has to give up both of its electrons. So if we go back a page, this magnesium would not be satisfied just giving up one of its electrons. It has to give up both. So if you're looking at something else, maybe boron, which would have 3 electrons, it would have to get rid of all of its electrons. You can't just give up one of them unless it only has 1. So this magnesium had to get rid of both of its electrons in order to satisfy the octet rule. So that being said, it needed to bond with 2 other fluorines. That's where we get this notation down here. So you had 1 magnesium and it's bonded with 2 fluorines. So the subscript of the 2 only applies to fluorine, and that's indicating that there's 2 fluorines bonded with this magnesium. Polyatomic ions. These are, whoopsie, let's go back. These are kind of like predetermined molecules that we'll be working with. So I have a polyatomic ion list that I have posted under like extra resources for this module, or sorry, for this unit. So if you go back to the modules and look for that, it's not going to be on the, well, I guess I can put it in the pages. I'll put it in the lesson as well, but just for easy access, it's going to be at the bottom of Unit 3 module, I guess. So I'll put that in there and you guys can see those. But polyatomic ions are ions that are made up of many atoms, which is where you get your poly and atomic, okay? We know that ions are charged particles, so that's kind of where this name comes from. It's many atoms of charged particles. So it's more than one atom that's chemically bonded, and the overall atom or the overall molecule has a charge. So examples of that could be down here. We have ammonia. It is NH4, okay? But the overall charge of this molecule is +1. Okay, so it's not like before, like when the example we just looked at was magnesium fluoride. You had 1 magnesium and 2 fluorines, but that balanced out, right? Because the magnesium was a +2 and each fluorine was a -1. So they balanced out to be a neutral atom. So here with the polyatomic ions, these are just molecules that have an overall charge of positive or negative. So ammonia, you have 1 nitrogen and 4 hydrogens. This ends up having an overall positive charge of +1. And then if we have sulfite, you're going to have 1 sulfur and 3 oxygens with an overall charge of -2. Okay, sorry, I'm trying to get these little menus to go away so you can see the whole screen. Okay, so the reason for that, if you look at sulfur on your periodic table, you'll see that it would have started out with 6 valence shell electrons. Okay, so it already has 6. And then oxygen also has 6. So if you're adding 3 oxygens and 3 sulfurs, or sorry, 3 oxygens and 1 sulfur, you're going to end up with an overall -2 charge. So then your covalent bonding, these are slightly different. So these are sharing electrons. They're not stealing, as one might say. So these are going to be between 2 nonmetals. Okay, so these are all going to be from kind of the top right corner of your periodic table. So the difference between these is that they are, the electronegativities are more similar. So you're not going to have one atom with a stronger attraction than the other, not significantly. So one might be a little bit stronger than the other, but they're close enough in attraction that each atom is going to keep its own electrons, but they're attracted to the other atom still. So here's an example of that. So you have 2 carbons. So if you look at these, the valence shell electrons only have 4 electrons on them. They're going to be sharing this pair in the center. So that's going to satisfy their octet rule. So for polar covalent, there we go. The difference in electronegativity needs to be between 0.4 and 1.8. So polar covalent means that they are sharing, but they're polar, which means that one end has a greater attraction than the other end. So if you're just bonding 2 atoms together, like in this example, you have hydrogen and chlorine. Chlorine has a higher electronegativity. It's going to be having more attraction than the hydrogen, but it's still not enough to steal the hydrogen electron. So they'll share. So that hydrogen is going to be sharing one of chlorine's electrons, and chlorine is going to be sharing hydrogen's electrons. So this satisfies the octet rule for both parties because hydrogen now has 2 electrons. And since hydrogen is so small, that satisfies its octet rule because it only has 1 ring. So 2 would fill it up. And then for chlorine, it needs 1 more. So it's sharing hydrogen's extra electrons. So now chlorine has 7 plus hydrogen's 1. So it has 8 valence shell electrons. So if you looked on that chart and you compared the 2 numbers, the difference between chlorine and hydrogen would have fallen between 0.4 and 1.8. Nonpolar covalent, there we go. Nonpolar covalent, the electronegativity needs to be, the difference needs to be very, very low. So less than 0.4, which means that the difference between them is they're almost equal in electronegativity, meaning that they both have almost equal pole from either side. So neither one of them is going to be having a stronger attraction necessarily, and they're going to be equally sharing the bond between them. So with chlorine, here you have, this example has 2 chlorines. They each have 7 valence shell electrons. So they can each share 1 electron with the other one and satisfy that octet rule. So here's just some kind of a chart, put it all together in one place for you. So the smallest form of an ionic bond is called a compound, and the smallest form of a covalent bond is referred to as a molecule. Okay, so those are fairly interchangeable. I've spoken with other chemistry teachers about this, and it's pretty well agreed upon that you can interchange these, but sometimes you would want to specifically be asked for a molecule versus compound, and this would be the difference. So ionic bonds are compounds, covalent bonds are molecules. So the bond formation for an ionic compound comes from the transfer of electrons. So you are removing an electron and transferring it into the other atom. For a covalent molecule, they're sharing electrons. Melting point for ionic bonds are going to be very high and low for covalent bonds because it's a weaker bond. It's easier to break with less energy. Ionic bonds are soluble in water, so these are like your salts. Covalent bonds are usually not soluble in water unless you have certain conditions where you force that to happen. Ionic bonds do conduct electricity, covalent bonds do not. Ionic bonds are typically comprised of nonmetals and metals, so you'd have 1 of each, and covalent bonds are going to be 2 nonmetals. And then the physical state of an ionic compound is usually a solid, where a covalent compound would be a liquid or a gas. Okay, so an example of that could be like covalent compound. An example would be like oxygen. So the oxygen we breathe is O2, so it's 2 oxygens. Obviously a gas, right? Another covalent compound would be, another covalent molecule would be water. Okay, so you have hydrogen and oxygens. So you have, that's also a liquid covalent compound. Ionic bonds are, the most common example is going to be salt. So if you have like a lithium chloride or sodium chloride, any of those combinations, those are going to give you crystalline structures. So they're going to be hard solids. So when we draw our bonds, we're going to start with Lewis dot diagrams of all the atoms involved. Sometimes you're going to have to figure out, do I need another one of these or not? And then for ionic, no, I'm sorry. Not right now. Okay. Lots of people coming in today. Okay, so for ionic bonds, you're going to have to draw the arrows to represent the transfer of electrons. So we're stealing electrons, you could say, or you're transferring electrons. So if you are showing the transfer of, let's say, sodium's electron over to chlorine, you would draw an arrow to represent that. Covalent bonds, you're still going to start with the Lewis dot diagrams, but you're going to draw circles around the atoms to represent sharing of electrons. And so I have, one more example of that. So here on this page, we're going to get into this stuff next class, but this is a good example of what I'm talking about for the covalent bonds. So here, if you have hydrogen, okay, they each need 2 valence shell electrons to be stable because hydrogens are small. And they're going to be sharing these electrons. So you would draw your Lewis dot structures. And in this case, with the covalent bonds, you want to position the electrons so that they are facing each atom so that you can show the bond easily. So here, normally, if you were just drawing a hydrogen atom, you would put that dot at the top for each of these. You could do that still for these drawings, but it's going to not be as neat whenever you're drawing the circles. So for the covalent molecules, you'll want to position these electrons so that they're facing each other because they are sharing. So these electrons will be positioned toward one another in an actual bond. So here we have hydrogen. You're placing these, your dots for the electrons towards each other. Then you draw a circle around the entire atom and include all of the electrons each atom is sharing. So this hydrogen is going to have a circle around the other hydrogen's electron and its own. And then this hydrogen has a circle around both electrons as well. And then over here for oxygen, we know oxygen has 6 valence shell electrons. So we know that each oxygen is going to have to share 2 electrons with the other to make up the octet rule. So this oxygen on the right needs 8, and so does the one on the left. So this oxygen has 6 already, and it's going to be sharing 2 of the other atoms' from the other atom's electrons. So we're going to draw a circle around this oxygen and all of its electrons and include 2 from the other atom. So this satisfies its octet rule, and then the same would happen on this side. Another example is nitrogen. So same thing. You're going to have a triple bond here. So you're going to have 3, they're sharing 3 electrons either direction. So you're going to position those so they're easily accessible from either atom. Draw your circles to represent the share. So we will talk more about this stuff next time with the lone pairs and things, but because this gets into bonding shapes and stuff. So what we're going to work on today is the ions versus the oxidation numbers of the ions, and which of these are going to be metals versus nonmetals, ionic compounds versus covalent molecules, and then the sharing for that. So if you give me 1 second here, I'm going to pull that up. Okay, so let's see if I can't switch screens here. I'm going to record this tab. Okay. So this is the assignment that you guys are going to have. So if we did the first one together, you'd have chlorine. You'd have to look at your periodic table and see that its atomic symbol is Cl. So you would fill that in. Its total number of electrons, let's move this up, get my periodic table out. Total number of electrons is going to be 17 as long as it's neutral, which as far as we know it is. So the number of valence electrons, you're going to be looking at the group it's in. So it's in group 17, so it's going to have 7 valence electrons, and the number of electrons gained or lost. Okay, so it wants to have 8. All of these want to have 8, right? So if it already has 7, it's going to be much easier for this atom to gain 1 more to satisfy its octet rule rather than to give up 7. That's just not going to happen. So it's going to gain 1 electron, which would make its oxidation number -1. Okay, so this is what you're filling in for this chart. The oxidation number gets people sometimes. So if you are gaining electrons, you're going to have a negative oxidation number. And if you're losing electrons, you'll have a positive oxidation number. So if I do another one, let's do magnesium. Okay, so magnesium is going to be Mg for its atomic symbol. Its total number of electrons would be 12. Its number of valence electrons is 2. So in this case, it's going to be easier for this atom to lose 2 electrons rather than gain 6 more. So it's going to lose 2 electrons. And if it's losing 2 electrons, it gives it an overall charge of +2. Okay, so that's what you'll do as you go through these. Let me see. Okay, so for these, like answering these questions, so are you going to have a positive or negative charge? Are they anions or cations? That kind of thing. So this is just vocab more than anything. So for your ionic bonds, these are the metal plus the nonmetal that have a very large difference in electronegativity. So the atoms are going to be transferring their electrons, a full outer shell, that kind of thing. So you guys can kind of work through these. But for these down here, what you're doing is drawing the molecules. Okay, so if I have, I'll do the magnesium one. So if I have magnesium is Mg, and then we have, let's draw a little circle here, make it a big one. Okay, so if I have Mg, oh, that was a big one. Never mind. Go back. That was a large boy. Okay, so I'm gonna have 2 dots here for magnesium. Okay, and then I'm gonna have iodine, and gonna put its dots on too. So iodine has 7. So we'd have, we'll do this in a different color. Okay, so we'd have 1, 2, 3, 4, 5, 6, 7. So one of these electrons from magnesium needs to go over to the other side. How many good colors? Okay, we'll do it with blue. Okay, so we would show that this electron would go over here. Okay, and in reality, you'd probably want to reposition these so that you'd have the open spot here to represent that a little bit better. So let me just do that. Erase that guy, replace him. Ow, ow. Not green. There we go. Okay. Sorry. So for here, this is an ionic bond. We're showing that the magnesium electron is transferring to iodine. Okay, so this satisfies this ion, this iodine. But we still have 1 more electron to get rid of over here with magnesium. We cannot leave it like this. Okay, so if magnesium has 1 more electron to lose, it has to give it up. So we're going to add 1 more iodine over here to satisfy that. So we're going to go in, we're going to put in our electrons. This is also going to have 7. That's kind of messy, but that's okay. Okay, and then we're going to show that this electron is moving over here. Okay, so that's how you would represent these. So for these, you just have to figure out, do you need to add another atom of something or not? So like sodium and chlorine, sodium has 1, chlorine has 7, so that will be an even trade-off there. And then you have more examples down here. So some of these are going to have more than others, like aluminum. Aluminum has 3 valence shell electrons and chlorine has 7. So you're going to have 3 chlorines to 1 aluminum. Then down here with your covalent bonds, these again are talking about, are you sharing or stealing? So we're sharing electrons in a covalent bond. They're between 2 nonmetals, all that kind of stuff. So here, if I have these, I have 2 hydrogens and 1 oxygen. So since we have 1 oxygen, we're going to put that oxygen in the middle. We're going to put the hydrogens on either side of that. Okay, because we'll talk about bond shapes a little bit more another time, not right now. So if I'm going to put in these electrons, so we know hydrogens have one, okay? So they're each gonna have one. We're positioning it so that they are kind of facing each other. Oxygens have 6, so we're gonna put 2 this way. Actually, I'm going to reposition that because each hydrogen only needs 1. So we're going to put 1 on each side and then 2 like this. So we have 6 electrons on oxygen, 1 on each hydrogen. So we know this is a covalent bond, so they're sharing. So if I draw a circle, make this transparent if I can. Yeah, that should be okay. I'll make it blue. This hydrogen needs to share. Ooh, the big fat one. Here we go. That's a big boy. Okay, so this hydrogen needs 1 more electron, so it's going to have its circle showing that it's sharing 1 electron from oxygen. And then you can draw another one over here to move that. Show that this hydrogen is also sharing 1 from that oxygen. And then for your, make this a little smaller, for your oxygen, you need another circle going around both of these hydrogen electrons like this. Okay, so this is not perfect. If I spent more time on it, I could make neater circles, but I just kind of want to get through this to show you guys. So that's how these will be positioned. So for the covalent bonds, it's going to tell you if you need more than 1 atom of something, like down here with carbon, you're going to have 4 hydrogens. So the carbon would go in the center, the hydrogens would surround it. And then you do have a challenge question down here if you'd like to try it. So this is what we're looking at for the assignment today. Give it a shot. Please let me know if you have any questions. Email me. If you do have a question about something specific, it would help if you tell me like which bond you're talking about, or if you screenshot your work. If you want me to check it, I'll double check it. So that is there for you. And that is all we're doing today. So let me know if you have any questions, and I will talk to you guys next time.